This presentation evaluates the application of artificial intelligence tools in enhancing whole-life costing for London's Liverpool Street Station concourse replacement. London Liverpool Street Station is one of the UK's busiest transport interchanges, accommodating approximately over 100 million passengers annually, projected to hit 140 million by 2025. As a Grade 2 listed structure, it faces heritage and architectural constraints that limit material modification and impose strict performance requirements. These constraints, combined with heavy pedestrian activity, frequent cleaning, and mechanical wear, make durability and low maintenance critical to operational performance. Any proposed flooring solution therefore had to balance technical suitability with architectural preservation and passenger safety. Working within heritage and architectural restrictions, this study applied artificial intelligence tools to enhance whole-life costing for large-scale infrastructure. Automated data generation, validation, and scenario modeling enabled faster, more accurate comparison of 5 flooring materials to identify the most durable and cost-efficient option. Whole-life costing assessed performance over a 60-year life cycle, while multi-criteria decision analysis ranked materials based on performance criteria. The project demonstrated how AI-supported data compilation and validation can streamline cost modeling while maintaining professional accuracy and ethical standards. 5 materials were shortlisted: granite paving, terrazzo tiles, epoxy resin, porcelain stoneware, and polished concrete. All 5 shortlisted flooring materials met the minimum performance standards for slip resistance, strength, fire resistance, and compatibility with daily cleaning. Whole-life costing was used to capture the full financial impact of each flooring option over a 60-year life cycle. This included the cost of installation, maintenance and cleaning, replacement and disposal, following the standards set by RICS. Alongside this, we applied multi-criteria decision analysis to assess each material across 5 weighted criteria. This approach ensured that short-term savings did not compromise long-term value or performance. AI tools were integrated throughout the cost analysis process to enhance efficiency, accuracy, and data consistency. AI tools including ChatGPT, Copilot, and OpenCost AI provided rapid generation and structured cost and performance comparisons. This enabled consistent assessment and significantly reduced the manual workload typically associated with cost modeling and lifecycle forecasting. AI-assisted automation streamlined the creation of the initial spreadsheet model. This model compared all 5 flooring options over a 60-year life cycle, factoring in 4 performance criteria. The Google Sheets AI plugin was used to perform net present value (NPV) calculations, applying the HM Treasury Green Book discount rate of 3.5%. This ensured future costs were expressed in present-day terms, allowing fair comparison between materials with differing maintenance cycles. The approach transformed WLC from a static calculation into a dynamic model capable of testing numerous operational assumptions in real time. Accuracy testing was critical to the project. All AI-generated cost data were verified against SPON's Architects and Builders Pricebook 2025. Significant cost variance emerged. Granite paving was overestimated by plus 420%, while polished concrete was undervalued by 45%. Discrepancies highlighted the risk of relying solely on generative AI for pricing. To ensure reliability, verified figures from SPON's 2025 were imported into the WLC model. This correction step brought all cost data in line with industry benchmarks. The scoring scale ranged from 1 to 5, with 5 indicating exceptional performance. Using ChatGPT and Copilot, AI tools structured and pre-scored 5 shortlisted flooring materials against key performance criteria. Durability carried the highest weighting at 30%, followed by 20% each for maintenance, safety, and sustainability, and 10% for aesthetics. Porcelain stoneware ranked highest with a score of 4, offering the best balance of durability, low maintenance, and slip resistance. Terrazzo tiles scored 3.90, valued for aesthetic quality and long lifespan, while granite paving matched 3.90, but was penalized for high environmental impact and maintenance costs. Epoxy resin and polished concrete, each achieving an overall MCDA score of 3.60, underperformed relative to alternative materials due to lower slip resistance and reduced impact durability, reflected in safety and durability scores of 3 out of 5. The AI-assisted MCDA improved speed, consistency, and transparency in decision-making, but required human oversight, especially for aesthetic judgment. The outcomes aligned with whole-life costing findings, confirming porcelain stoneware as the most durable and sustainable long-term solution for TfL's London Liverpool Street Station. To assess passenger movement patterns, Copilot was used to generate an AI-produced heat map of footfall across the concourse. The tool processed simulated entry, exit, and dwell time data, quickly identifying high-traffic areas, with red zones representing the busiest parts of the station. This provided an instant visual interpretation of pedestrian density, something that would traditionally require manual observation or CCTV data analysis. Despite this, the AI correctly identified the central concourse as the area most exposed to continuous footfall. That insight validated the model's analytical potential, especially for highlighting where maintenance and cleaning demand would be greatest. This example clearly demonstrates the variability of AI performance, powerful for prediction and visualization, but dependent on human expertise for validation and correction. It reinforces the importance of reliability checks and continuous supervision when deploying AI for visual or spatial assessments in infrastructure projects. AI significantly enhanced both speed and analytical scope. Tasks such as data validation, cost comparison, and scenario modeling that once took hours were completed in minutes. Tools like ChatGPT, Copilot, and OpenCost AI generated structured data instantly, allowing the team to prioritize interpretation and verification over manual processing. Consistency also improved, as identical algorithms were applied across all materials, reducing human bias in cost ranking and performance evaluation. However, limitations were identified. AI lacked contextual awareness, illustrated by inaccurate heat map outputs, showing that expert judgment remains vital for interpreting site-specific conditions. Accuracy was further constrained by input quality, as AI only performs as well as the data provided. Once validated, results became robust and reliable. Ultimately, combining AI automation with professional oversight delivered the best outcome, achieving speed, transparency, and cost efficiency, while ensuring compliance with RICS standards and maintaining defensible, evidence-based conclusions. It became clear that human expertise is vital in feeding verified, context-specific data into AI systems. AI on its own lacks environmental context, which makes human judgment indispensable. The input of verified data proved essential for ensuring model accuracy. When the team cross-referenced AI-generated outputs with established sources, such as SPON's 2025 cost data, discrepancies reduced significantly. In terms of efficiency, AI tools eliminated the need for slow manual data entry, automating repetitive calculations, and freeing up time for deeper analysis. This increased both productivity and precision, minimizing human error in cost modeling and lifecycle projections. This compliance was crucial for maintaining ethical standards and professional credibility when applying AI within a regulated environment like TfL's infrastructure projects. These reflections confirm that while AI accelerates data processing and improves analytical scope, expert interpretation remains critical. Human judgment bridges the gap between raw computational output and real-world decision-making. Validation began with a site visit to London Liverpool Street Station to cross-check AI-generated assumptions on footfall, material wear, and cleaning intensity. This confirmed that while AI produced reliable cost forecasts, spatial and behavioral predictions required professional adjustment. AI outputs were then verified against SPON's architects and builders' pricebook to benchmark costs within acceptable tolerance ranges. RIC's whole life costing and sustainability guidance ensured the financial models aligned with recognized professional methodologies. Further checks against Network Rail's asset management standards and BSN specifications validated compliance for safety, fire resistance, and mechanical strength. Together, these layers confirmed that AI-generated data satisfied RIC's, British standards, and Network Rail requirements, producing results that were both technically accurate and operationally viable for live infrastructure environments. The future of AI in whole life costing lies in its integration across TfL's asset renewal frameworks to support long-term investment planning and reduce project planning time. Expanding AI-assisted tools would enable continuously updated lifecycle models as asset performance evolves. Although AI can automate cost modeling and forecasting, it still requires human oversight to guide data inputs and interpret contextual factors such as maintenance schedules and operational constraints. Professional verification therefore remains essential to ensure accuracy and reliability. Linking AI with TfL's BIM-based asset management systems could enable predictive maintenance and real-time cost forecasting. Future adoption must comply with RICS responsible use of artificial intelligence in surveying practice, ensuring transparency, accountability, and ethical governance. As AI learns from verified data, predictive accuracy will improve while reducing manual checks. The most effective model will remain hybrid, combining AI's computational efficiency with professional judgment to maintain ethical, reliable, and sustainable management of public infrastructure assets. These are the references used to validate the study. Thank you for listening.